In Chapter 3, we talk about developing a program. Developing a program is actually a pretty interesting subject. I have found from personal experience that one's tendency is just to dive in there and start writing code. And 9 times out of 10, that doesn't work out too good. On smaller programs, sure. But if you get involved in a pretty big project, you're going to end up dead in the water pretty fast. So we'll take a minute and we'll talk about the whole notion of developing a program. Developing a program requires a programming cycle, a development cycle, which is mentioned in Chapter 3. It involves problem-solving principles and actually writing the program. The first thing is you need to completely understand the problem, okay? Good luck. I don't know anybody that completely understands a problem, but at least understand as much of it as you possibly can. Then, once you have the problem understood, devise a plan to solve it. Once you have a plan devised, carry out the plan. Okay, and I would actually say here, try to carry out the plan, because it probably won't work. Okay, and then lastly, you review the results of trying to carry out your plan. So how does this all fit in with writing a program? Well, first of all, we analyze the problem. Then we design the program using pseudocode or something like that. Then we code the program, and then we test the program. So let's begin with analyzing the problem. All right. I ended up with an interesting comment that came to me through the email, and that was a person, when we were doing an assignment, figuring out what degrees Fahrenheit was if you were given degrees Celsius. The person said, "Why can't I just cast everything to integers?" Because I dinged this person a point for doing that, and really the biggest reason is we never asked the client. We never asked the client what degree of precision that we're working with, and if you're not going to ask for the degree of precision from the client, you always go with whatever the computer says. You know, if the thing is outputting in 6 degrees of precision, then that's what you output, because you don't want to make a mistake and give what the user or the client thinks is accurate information when in truth it's not. For example, let's say we have 9.8. and we cast that floating point number to an integer. What it's going to do is it's going to return 9. It isn't going to round it up to 10. Well, that is way more wrong. You know, 9 is more wrong than 10 is. And we don't want to do that to a client. So we have to identify the desired results. What is the output that we're looking for, right? Once we identify that, then we determine the input we need to produce those particular results. In your slide series here that we have, they create a program that will generate 6 numbers to play the lottery. Is all 7s okay? Probably not. Is a -3 and a 0, 8, 9, blah, 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 is that okay? Lotteries tickets don't usually have negative numbers, right? Is 1, 2, 6, 47 point blah 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 or 93.45, is that okay? Probably not, because lottery tickets tend to only use integers, right? So we have to find out from the client what is okay for our lottery ticket program. Here we have a suggestion. The desired results are 6 different positive numbers within the range of 1 to 40. Okay. I've never bought a lottery ticket, so in truth I have no idea what they require. So once we've done that, we design our program. In order to design the program, we're going to use charts, models, or ordinary language, such as pseudocode, okay? And then we're going to identify the algorithms needed. What exactly is an algorithm? An algorithm is a step-by-step method to solve a problem or complete a task. They must be well-defined, they must be well-ordered, they must produce some result, and they must terminate in a finite amount of time. Okay? Algorithms, in truth, are the magic behind writing code. And in most cases, we use equations to develop algorithms. So let me move over to this little slide series and I'll go partially through this. All right? So, anytime you use a digital device, you are enjoying the result of implementing an algorithm. Whether it's your iPhone, whether it's a desktop computer, a laptop, whether it's an Android, whether it's your watch. You are enjoying the result of somebody's effort at implementing an algorithm. It's going to be something that involves a step-by-step process that can be described using an algorithm. Okay? So what is it? Well, I told you what it is, right? So let's break it into parts. The parts are an ordered sequence, as I said. Here's something that I didn't mention before, is unambiguous and well-defined instructions. There has to be absolutely no doubt as to what you need to do when you're implementing an algorithm. That's why a lot of algorithms are described using mathematical equations. All algorithms will perform some task, and all algorithms will stop running at some point. They have to, right? Otherwise, you'll never get a result. For example, let's say we use a peanut butter and jelly sandwich, all right? The flowing of one thing after another. That's going to be the algorithm. That's what we're going to talk about here, the ordered sequence. Peanut butter and jelly sandwich, well, helps to take the lid off the jar of peanut butter first, right? Helps to put the knife into the peanut butter. And if we fail to do these steps in the correct order, you're going to result in operational failure. It's not going to work, right? You're going to end up scratching up the lid with your knife or whatever. Or if you're really aggressive, you may end up poking holes in the lid with your knife. It needs to be unambiguous. Ambiguous means that it is open to having several possible meanings or interpretations, right? Each step can only have one meaning. Take the lid off the jar. Pretty clear, right? That works fine if there's only one jar, but what if there are two of them that are nearby? You have a jar of pickles, you have a jar of peanut butter. Let's go ahead and pop the lid off of the pickle jar, because, hey, I like Vlasics anyway, right? And then go ahead and try to smear that on your bread with a knife. Ain't gonna work too good. So we need to make sure and clarify by saying, take the lid off the peanut butter jar, okay? It performs the task and halts in a finite time. Algorithms begin with the end in mind, right there. They begin with the end in mind. You must know what the task is that you wish to perform before you can start making an algorithm. And what we mean by that is we know what we need to accomplish, and we know what we're going to have in order to accomplish whatever it is that we need to accomplish. Consequently, we now know what our input is. We now know what our desired output is. All we have to do is come up with the steps to get the output based upon the input that we have available to us. If you don't know that the goal is to make a peanut butter and jelly sandwich, well, you're pretty much toast, right? There's no way you're going to be able to figure out how to make that thing. Okay? And of course, it has a finite amount of time. If you didn't finish the algorithm, you would never get to eat the sandwich, and consequently, you would starve to death. Of course, for some people, peanut butter and jelly sandwiches are pretty nasty, so they would rather not eat the thing. Go ahead and let it halt prematurely, but don't let it go on forever, right? So you must decide when an algorithm is finished. Does it end when 2 slices of bread are put together? Does it end when the sandwich is sliced in half, corner to corner, or in half side to side? Does the algorithm end when everything is put away and cleaned up? You have to make that decision, okay? And in truth, good programmers are going to end the algorithm when everything is put away and cleaned up, okay? Now, having said that, let's go ahead and move back to where we were, okay? So the next step after we come up with our algorithm, and we're pretty happy with that, we go ahead and we code our program, okay? And the way that we code the program is we're going to translate the charts, the models, the pseudocodes, or ordinary language into program code, which you've already done to some degree, right? You did an algorithm for calculating degrees Fahrenheit from degrees centigrade, and you went ahead and you stuck it into Python and you stuck it into Raptor. And probably many of you, quickly realize that the pseudocode that they're asking you to do in the book doesn't line up very well with the programming language that you actually have to use to implement the algorithm. And this is going to be the case in most situations. The language often does not perfectly match pseudocode. So we have to kind of keep an idea of what's going on with the language, right? So I have here a little red squiggly on documentation, which means it's spelt wrong. Okay? So Add statements to document what the pseudo or what the code does. This is something that I personally do. Okay. If I have something that is pseudocoded, I take the pseudocode and I put it into my programming language as comments. That way I never miss a step, and at the same time all my code is commented. So I'm going to have like a step, get the degree centigrade. That's part of my algorithm. And then the next step will be, convert degrees centigrade into degrees Fahrenheit. That's another step of my program. And then finally the output would be deliver the answer to the user. Okay? Well, guess what? Those are great comments, because the part where you do, where you say convert degrees centigrade into degrees Fahrenheit, you just put a little, if you're in Python, you just put a little hash symbol in front of that and then put the formula underneath it, and there's absolutely no confusion whatsoever with respect to somebody else who is looking at that code. They're going to look at that thing and they don't even need to know about the formulas involved in converting from centigrade to Fahrenheit to understand that code, because there's that nice, neat little comment that is above it. Now, those of you who handed in the Fahrenheit program earlier, I dinged you a couple points for not putting a comment on that line, because we really want to know what that formula is doing. Okay, so after we code the program, we want to make sure that we've followed the good old rules of syntax. Okay, we put in our comments, they become, or we put in our algorithm, they become comments. Now we're going to start coding everything. We absolutely have to follow the syntax. Now, yours truly, which would be me, I have lots of programming languages that are floating around in my head, and I have to tell you, probably about 90% of the time I type in the wrong command, or I use the wrong syntax. So what exactly is syntax? Okay, well, in English, let's say that you're going to talk about a cheese sandwich. We'll get away from peanut butter and jelly and go to probably a worse tasting sandwich, cheese, unless it's grilled cheese, which is actually pretty good, especially if you put bologna in there or something. Of course, I digress. So let's get back on topic here. So you're telling your friend where you put the cheese sandwich. I have put it on the table. Okay? Incorrect use of English syntax to say, or would be to say, I have it on the table put. You see, I can't even say it incorrectly. I have it on the table put. Well, all the right words are there, but the proper syntax, it's kind of messed up, and for some people, that sentence doesn't even make sense. All right? But if you translate it word for word, the second sentence works perfectly in German. Okay, so from one programming language to the next, syntax is going to be different. And we have to look out for those things. And one of the things that's really, really cool that you're going to learn about later on in this semester is that whatever development environment that you're using for writing your program, it has a thing in there that's called CodeSense. And as you write your commands, and as you write down syntactually correct commands, or maybe syntactually incorrect commands, there's going to be a little dialog box that's going to pop up, and it's going to be taking guesses at what it thinks you really want. It's going to give you some great clues as to what the correct syntax for a language is, because in truth, who can remember it all, right? So once we write the program, we want to test the program. This is called the analysis phase, all right? Did I interpret the data correctly? Does the program fulfill the requirements? Are there any formulas or procedures that I forgot or that I need to correct, or something along those lines? In the design phase, it really, really helps to use what's called desk checking to walk through the program. And basically what that is where you sit down and you write out the program on paper. You just follow it out on paper without even involving a computer. And I see that my timer is about ready to run up. So let me pause right here and move into another recording.